So this is the second video for section 14.1. Today we're going to be talking about two kind of more specific examples, and these are what are called distinguishable permutations and combinations. So let's just start off with a little bit of review from what we did in the last video. So the first question here, just a simple kind of example of the counting principle. How many ways can 3 history books, then 5 math books, then 7 art books be placed on the shelf? So it has to go 3 books for the 3 history, then the 5 math, then the 7 art, but the order of those can be arranged. So video pause and then come back and we'll talk about that. So with something like this, we're going to start off with thinking about the 3 ways you can place the history books, separate from the 5 ways you can place the art books, separate from the 7 ways that you can place the, sorry, I said art books first, but 3 history, 5 math, 7 art. And so we can think about those. There'd be 3 ways to place that first history book, then 2, then 1. Same here, there'd be 5 ways to place that first math book, then 4, then 3, then 2, then 1. And then the same thing here, 7 for the first one, 6, 5, 4, all the way down. And so what we basically got here is 3 factorial ways to place the history books, 5 factorial ways to place the math books, and 7 factorial ways to place the art books. And the question is, well, what do we do with those 3 numbers? And because they're completely independent of each other, we're actually just going to multiply those together. So 3 factorial times 5 factorial times 7 factorial. That's something I'm definitely going with Desmos for. 3 factorial times 5 factorial times 7 factorial. And it looks like we've got a little over 3.5 million, 3,628,800 different ways we can place those books. Now for our second one here, how many ways can the top 8 finishers place in a race with 52 people? Now this one is a straight up permutation here. We've got 52 people, we're taking 8 place finishers, and because there's a difference between finishing first and second and third, we're going to use what's called a permutation from yesterday. And so all we've got to do here is 52 permutations of 8, and we can let Desmos handle that. But remember, what all that is going to be saying, well, there's 52 places in the first spot, 51 places in the second spot, 50 places in the third spot, and so on. But a permutation, that's what that is going to be a little bit faster than calculating that all out. So I've got 52 people, I need to pick 8 of them, and you can see I've got quite a bit here. 10 to the 13th, I believe, is, we're over trillions, I believe, at that point. I think 10 to the 12 is trillions, so we've got like 30 trillion possibilities there. Okay, so let's take a look at something a little new. How many ways can I rearrange the letters of the word bookkeeper? And so if you look at bookkeeper, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, you might think, oh, well, that's going to be 10 factorial, because I could have 10 spots, 10 letters in the first spot, then 9, then 8, then 7, 6, 5, 4, 3, 2, and 1. But the problem with something like the word bookkeeper is that there's repeat letters. There's 2 O's, 2 K's, and 3 E's. And so just using this as an example, if I changed places of those 2 O's, would the word be any different? Or if I changed the places of those 2 K's, would the word be any different? No. And so we have to take that into account. So rather than there being 10 factorial ways, there's actually slightly less ways that we can do this. And what we're going to do is just divide out the different possibilities. So the O's and the K's are fairly straightforward. Just switching the O's just means that basically half of our options are not going to work anymore. And so we basically have to just divide that by 2. Switching the 2 K's around would mean that basically half of our options again are not going to work, so we need to divide by 2 again. But then how many different ways can we replace those E's? There's 3 E's. How many different orders are there for those 3 E's? And again, that's basically a factorial. Turns out if there's 3 E's, there's 3 ways to place the first E, then 2 ways, and then 1 way. And so we've got 3 factorial. And what this is actually thinking about here is these 2's are actually 2 factorial. It's the same thing as 2. And so what we've got here is kind of a formula for figuring these out. And so we're just basically dividing out the ways they can be the same. And so this is called a distinguishable permutation in your book. The idea here is because some of those items are indistinguishable from each other, we can't count them separately. We have to account for the fact that they are actually the same thing. And so here's our formula for distinguishable permutations. If we have n items, in our case we had 10 letters in the word bookkeeper, and n1, n2, n3 of them, etc. are the same. In our case that was the O's are the same, and the K's are the same, and the E's are the same. Then we can use this formula. So we had our 10 factorial on the top, and then because there were 2 O's, we had 2 factorial. There were 2 K's, so 2 factorial. There were 3 E's, so 3 factorial. And even in this case, technically the letters that were, there's only one of them, like the B and the P and the R are still in there too. We just have times 1 factorial, times 1 factorial, times 1 factorial. But that's just 1, 1, and 1. And so we usually leave those out. But technically in this case, in the formula sense, they're in there. We include them for every single thing. And so we'd have that formula right there. 10 factorial over 2 factorial times 2 factorial times 3 factorial. And if you want to list out the ones, you can, but don't put those in the formulas. So if we go over to Desmos, we can do that. Oops. 10 factorial divided by 2 factorial times 2 factorial times 3 factorial. And as you can see here, if I just put in the times 1 factorial, nothing is changing. Right? So I don't need those at all. But we have 151,200 different ways to rearrange that word bookkeeper. and that's right there, that's our formula. So let's take a look at one more example here. There are 5 red marbles, 3 green marbles, and 7 blue marbles. How many distinguishable orders can they be placed in? So hopefully you got that one right. But again, the same kind of thing here. We've got a total of 15 marbles, so that's our capital N on top in that formula. 15 factorial. But because 5 of the marbles are the same color, and then 3 of the other marbles are the same color, and then the final 7 are the same color, we have to include those 2. And so when we go back over to our formula, we've got 15 factorial divided by 3 factorial times 5 factorial times 7 factorial. And we get a total of 360,360 different ways that we can rearrange those. Taking into account the fact that just changing around those 5 red marbles doesn't change anything, or the green marbles or the blue marbles. Now the last thing we've got to talk about here is what are called combinations. Now combinations are basically just a more general case of distinguishable permutations. Actually, I guess more specific, that's the wrong word there. In the case here, all of the items are considered the same. So you'll a lot of times see this as using an example with a committee in it. All of the members of a committee are the same. They're all equal to each other. All the not members of a committee are going to be the same as well. And there's no distinguishable difference between one member of the committee and someone who's not a member of the committee. And so if we think about this like a distinguishable permutation, we've got 30 people to pick from. That's our capital N. We want 3 people in our committee. Those 3 people are not distinguishable. And what that means is there's also 27 people that are not in our committee. Those 27 people are, again, not distinguishable. Switching those people around doesn't actually change who's in the committee. And so that would be how we'd find this number of people. Another way to think of this, if you look at this part of it here, that's the same formula we'd have for a permutation, something like picking a president, vice president, and secretary from those 30 people. But because we don't have separate positions, they're all just equal committee members, we're dividing by the number of ways that you can rearrange those 3 people. So there's 2 ways to think about that. I tend to think about it the way I just described, but it's also interesting to think about that as just another kind of distinguishable permutation. So what we've got here is our formula for combinations. So n combinations of R, or n choose R sometimes, is going to be n factorial on the top. N is the number of things you have total. R is going to be the number of things you want to pick, which means n minus R is the number of things left over. So using that formula, let's go ahead and try to do one that's a little bit more complicated. So here we've got a class of 15 seniors and 10 juniors, and we want to make a committee with 3 seniors and 2 juniors. Now this one's actually got combinations of both types in it. It's partially a combination and partially a permutation. So let's split this up. If we thought about our seniors first, 15 seniors, a committee of 3 out of those. That's just going to be 15, choose 3. Then we've got our juniors. There's 10 juniors, and we're going to choose 2 of them. So 15, choose 2. Within each of those separate groups, the order doesn't matter. The 3 seniors can be ordered however you want. The 2 juniors can be ordered however you want. But between the 2, they do matter, because these can only be the seniors and these can only be the juniors. So between the 2, I've got to multiply them. So it's like a permutation of combinations. So this one, if I go to Desmos here, again, Desmos has this formula in it for you. Got to put the formula in first. So I've got 15, choose 3, and then I'm going to multiply that by 10, choose 2, and then I've got my total of 20,475 different options there. Okay, so let's do one more. So let's say we've got a class of 30 people. I want to pick a president, a vice president, a secretary, and 3 committee members. Let's think about how many different ways we could do that, and then we'll come back and talk about it. Okay, so this one's kind of, again, a combination of a permutation and then a combination. So these first 3 people, the president, vice president, and secretary, are distinct positions. That's going to be a permutation. So what we've got there is something like 30, pick 3. Then we've got our 3 committee members. Those are going to be a combination. Now, at this point, we've already picked the 3 president, vice president, and secretary, so I only have 27 people left. So I'm going to do 27, choose 3. And then again, because our president, vice president, secretary, and our committee are different people, we're going to go ahead and multiply those together. So again, we've got a combination here between a permutation and a combination. And we can go to Desmos and type that in if we wanted to. Okay, so at this point you've seen all of the examples. You've got, I think it's going to be about 10 homework questions here that you'll have to do. Remember to make sure that you're showing all of your work and making sure that I can find the work and the answers, and it's neat enough for me to grade online. We have our office hours on Tuesday, I believe I said from 10 to 11, and on Thursday from 1 to 2. So feel free to stop by there if you have any questions. And these are going to be due next Tuesday.